Hey, chemistry, how you doing? We are jumping into another flipped lecture here, and we're going to be continuing the conversation about what makes reactions go. In the last lecture, we looked at the contribution of energy, and here we're going to be looking at the contribution of chaos. Yes, chaos. Everything is chaos, especially in chemistry. Here we go. When we look at the question of will a reaction occur, there's more to it than just energy. Last time we talked about energy flow, and we said that reactions that release energy, that are exothermic, are more likely to happen than reactions that are endothermic, that absorb energy. You've got to feed them some energy for the reaction to happen. But it's not a hard and fast rule that endothermic reactions don't happen. They do happen. Your ice packs that you use in your first aid kit is a great example of those. So lots of times reactions do occur that need to absorb energy, and in those situations, then the consideration that makes those happen is a question of, is there more or less chaos after the reaction than before the reaction? So chaos, disorder, is another factor. Okay, let me show you an example here. This is a spontaneous endothermic reaction, and the video I'm going to show you, this is not my video, right? Disclaimer, this is not me. And this person has his own disclaimer, don't do this at home, you could hurt yourself. But what he's got here is a thermometer, and he holds it up real fast and you can't see, but it's a thermometer and it's some, coolish temperature. And what he's putting in is a mixture of sodium bicarbonate and citric acid, and those are both dry powders, okay? And he's combining the citric acid and the sodium bicarbonate. So far, no reactions happening because he's just putting two powders next to each other. Then he's going to show you the temperature, and it's too fast to see. But when he adds the water, now these two substances dissolve, and a chemical reaction spontaneously happens. You can see that gases are given off, it foams and it bubbles, and now the thermometer, now you can read it, it's at about 5 degrees. It came down in temperature quite a bit, and if he were to keep doing this, he could get it down to like near zero. You can actually make water almost freeze by doing that. So that's an endothermic reaction. The reason that the reaction happened is because the degree of chaos after the fact was much greater than the degree of chaos before the fact. Before, you had dry powders, which are pretty organized things. Afterwards, you had gas, which is moving, volatile, flying out of there. That increases disorder. And so there's more chaos, more disorder afterwards. And an increase in disorder always favors a chemical reaction. So we call this measure of randomness in a system, it's entropy, and we use the letter S to represent it in equations. So the calculation for calculating entropy, change in entropy, is exactly the same math, and it's done exactly the same way as calculation of enthalpy. So sometimes it gets confusing, because both instances you need to look up on a table what's the value for S for this substance, and then you subtract all of the products minus all of the reactants, and you get a term. And that term will tell you if chaos has increased or decreased. Now, tables are a little bit more complicated for entropy because the state of matter matters. Water is more chaotic as a gas than it is as a crystal, so you've got to look up not just the substance, but what state of matter it's in to get the right value for S. Okay? So in this case, you want a positive delta S. That means that the products have more chaos than the reactants, which means that chaos increased, and chaos increasing not only favors, all the villains in comic books, but also chemical reactions. Alrighty? So increasing or decreasing enthalpy, the heat, is a part of what the answer to the question, will this reaction happen? Increasing, decreasing entropy is another part of answering the question, will this reaction happen? So, of course, we get to put them together and do more math. You get to do some math to get a delta H, then you get to do some math to get a delta S, and then you get to stick your H and your S together and ask the question, what temperature is this starting at? And get a new term called delta G. Delta G stands for Gibbs. At least that would make sense. S and chaos, H and heat, at least that works. But H and entropy, G and Gibbs, at least I can remember that, right? G and Gibbs. Gibbs free energy. Gibbs is the last name of the chemist who came up with this. So the the form of measurement is named after the chemist. Delta G equals delta H minus T delta S. So the change in free energy, delta G, is equal to the change in heat energy minus a multiplication of the temperature that this reaction begins at, not ends at, because we're going to have a delta H thing that goes on, right? And delta S, the change in entropy or chaos. So you've got to be in kelvins for this. Keep that in mind. This does not work in Celsius. You can't have a negative T. Okay, here we go. The more negative the value for delta G is, the more likely it is to occur spontaneously. So a very large negative delta G number, the reaction is going to pop. A small negative delta G number, the reaction is going to probably happen, but it'll trickle along. A small positive, a big positive delta G, the reaction is unfavorable. You've got to stand on your head and do crazy things to get the reaction to happen. So the larger the delta G, the less likely. The smaller the delta G, the more likely. So these next four slides, you can, or points on the slide, you can either just write down, or you can just say, oh yeah, I get it. If you have an endothermic reaction, so that means energy has to be added to the reaction, so that's a positive delta H, and you have decreasing entropy, so you have a negative delta S, then a positive number minus a negative becomes even a more positive number, right? Subtracting a negative is an addition statement. So you get a very large delta G. This is very unlikely to occur. You'd have to do crazy things to make that reaction happen. Okay? If it's endothermic, so it has a positive delta H, but it's increasing the entropy, so positive delta S. Now you have a positive number minus a positive number. As long as the second positive number is bigger, you could still get a negative delta G. So that might be spontaneous or might not be spontaneous. Same sort of situation if it's exothermic. It gives off heat, negative delta H, but it has decreasing entropy, so it's a negative delta S. Now you have a negative number minus a negative number, which turns into a negative number plus a positive number, right? As long as the negative number is larger in magnitude than the plus of the delta S, then you still get a negative delta G, and the reaction might be spontaneous. The money shots are the negative H minus a plus delta S. Exothermic and increasing entropy, that's when you are definitely going to get a negative delta G, and that's where the reaction will be spontaneous at every temperature. Okay? Let's do a very long example. Take a deep breath. Hold it for about 20 minutes. No, just kidding. Take a deep breath and let's jump into this. Is the following reaction spontaneous at 0 degrees Celsius, which is 273 Kelvin? Okay. Silver oxide, Ag2O, plus 2 moles of hydrochloric acid. So you take silver oxide, you drop it in some hydrochloric acid, and what we wind up getting is a salt, silver chloride, and water, H2O. In this case, just as a little reminder, in this case, silver oxide is acting as a base. But we're going to have this reaction where the silver hooks up with the chlorine and the hydrogen hooks up with the oxygen. We wind up with water and silver chloride. Does that happen? Or would it not happen? So this is very cold water. This is cold water that's, if you took any more thermal energy away from it, it would turn into ice. So really cold water, hydro flask water, right? So there's not a lot of free energy available here, but we're going to see if this reaction will happen. So first, we need to look up the enthalpy and entropy values for the substances involved, and that is just going to a table. So let's go to the table. And this table is in your book, and you could look it up, and so we just find the 4 things we need, right? And there they are. Silver chloride, here's the enthalpy, here's the entropy, enthalpy, entropy for silver oxide, hydrochloric acid, and water. And we look them all up. Now notice the terms are different. That's going to come into play in a little bit. This is kilojoules per mole, and this is joules per mole degree Kelvin. So kilojoules and joules, we're going to have to adjust for that later on. So just keep that in mind. Okay. So here we go. These are my values. I just got them from a table. I copied them down from the table and wrote them down. Okay. Now we're going to do delta H first. Sigma delta H products minus sigma delta H reactants. So Products. The products, water, 241.8, water, 241.8, okay, plus 2 of hydrochloric acid because, 2 of the silver chloride. Because the silver chloride here has a coefficient of 2, I got to carry that down. 2 times the negative 127, here's the silver chloride, there's the negative 127, right? Minus the sum of negative 31.1, that's the, so now I'm in the reactants, now that's the silver oxide, right? There it is. Plus 2 times negative 92.31, 2 times hydrochloric acid, there's that. This is not hard math. Multiply, add, subtract. And I wind up with negative 280.08. That's a pretty big negative delta H, which means that silver oxide into hydrochloric acid releases a lot of energy. So that's good. That's good. Negative 280 kilojoules. That's a good amount of thermal energy per mole. It's looking good for this reaction at this point. Okay, I'm going to move my little picture over so you can see it better. And now we're going to move on and we're going to calculate delta S. Okay, so I need to look these up in the table and just put it into that equation. When I put all these values in, I have the sum of the products, and again, it's just the water, which was right here, plus twice the silver chloride, which is right there. Just kidding, silver chloride, I keep doing that, is right there, minus the sum of the reactants that I put those numbers into. So same exact math, multiply, add, subtract. So I have here negative 113.7. Now this is joules per mole. Notice that, joules per mole, kilojoules per mole, I can't leave it that way. I have to have them in the same terms. So my joules per mole, Kelvin, I need to convert to kilojoules per mole, Kelvin. So let's convert negative 113.7 joules to kilojoules. That's easy, right? So that's negative 0.1137 kilojoules per mole Kelvin. Now I'm in the same terms. Now I can move on with life. Delta G equals delta H minus T delta S. So delta H is this negative 280.08 kilojoules per mole. Delta S is the negative 0.1137 kilojoules per mole, Kelvin, and then I'm going to have this temperature term in here, and I was told that it's 0 degrees Celsius or 273 Kelvin, so the 273 Kelvin goes in there. That corrects for this. So now I'm going to multiply here, and that's exactly the same thing. I don't know why I did that. I'm going to multiply here, and then I'm going to subtract. This is subtraction of a negative number, so that's addition. So I put them together, and I have a negative delta G, negative 249.0399. It's a very large negative delta G, which means this reaction is very spontaneous. It will jump to life when you pop it together. So that's the way that we do these Gibbs free energy equations. None of it is hard. It's just a lot of easy math. Okay, so hopefully that clears it up for you. If you have any questions, please put them in the comments field below, and I will get to them as quickly as I can, or you can talk to me tomorrow, and we will work through it together. Jesus loves you, and so do I. I hope you have a wonderful evening. Good night.